and is literally like 97 degrees again. It's the middle of starting October. It's still okay. Well, at least I'm ready to record. Want to continue on our data structure studies, and this time instead of creating a stack with arrays, let's actually create a stack with linked lists. So I'll get the project set up right now. Let's see, stack linked. Where is it? Uh, stack linked list. Okay, so we'll have main.c. I'll just change directory, get myself all set up. Okay. All right. So we were at the whole memory leak thing last time. Alrighty. Okay. So let's review what a linked list is, so that we're all on the same page. Basically, linked list is just some sort of data structure. Pretend these are like little data structures that contain, let's say, some sort of value in them. And at the same time, they all have a pointer to some next node. Now, I usually, in most examples, examples will show you kind of like a linear, pointer to from one node to another. But I think that's like sort of misleading because it kind of hints that linked lists are sort of contiguous in memory. And so I like to just confuse myself sometimes and draw it like this. And if let's say you order this as like, let's say we say this is 1, 2, 3, 4. So it's like a linked list of integers. So, we were to reorder this, it's just basically something like 1, 3, 2, and then 4, and then null. So these two, number 1 and number 2, are the same. It's just that one is kind of all over the place in memory, and that's true. It's just it doesn't really matter how they're arranged as long as you can get from one end to another end. So 1, 3, 2, 4. It doesn't really matter how you sort of represent that as long as that's true. So that's why we tend to just draw our linked list in order like this, conveniently, like a timeline, but not really. So in code, normally, that's sort of like a struct. So we like to usually do something like this. Then we'll say it holds a value, some sort of value, and then also recursively some sort of pointer to a next node. That itself represents a linked list node. So that we do something like this, node n equals something like dot value is 5. Then what else we have? Dot next is null. That creates a node that looks something like this. And normally what we do is we like to track our head. So we do something like head equals null. So node head equals, not null, node head equals n. So then we'll have another variable that sort of keeps track of our head. And we could do the same thing with tail. For example, we wanted to keep track of a tail. So like at the end of the linked list. So then we can say that's the end of the linked list. It's also the start of the linked list. To insert a link into a linked list, for example, let's say we have our 5 again. And we want to insert something like 6, for example. Well, we had our head here, and we had our tail here. We could sort of say, okay, well, let's have whatever we have for tail, and actually set the next of our tail to be this new node we're going to create, and update our tail to be the new node that we created. So first, let's create our new node. So first is create a node. Okay. And by default, that points to null. Then what we want to do is set tail dot next to be our new node. And then tail is then updated to new node. Or, better yet, equivalently, tail dot next. So let's work that out. So we create a new node. Now we want to set tails next, or tails next. So this one right here. So that's tail. To this guy. I don't know why I drew my arrow like that. Really, it's like this. Pointing to this node here, not the value. And then what we do is we update tail. So get rid of this. Oops. Get rid of this. Get rid of this. Well, I shouldn't have gotten rid of that. Update tail to point it here. So we follow this pattern. So create a new node 7 will be to basically create a node here. Okay. And then once we've created the node, we set tails next. To be the new node here. Then we update tail to be tails next. So tails next is this one. So we update that to now be here. So we repeatedly do that to kind of insert into the end of the list. We could also go the opposite direction too when we insert. So let's say we had 5 as our node. That points to null. And then we had, again, head. We also have tail. Let's say we want to insert 6 again. So what we'll do is we'll create a new node 6. Okay. And instead of having tail, what we'll do is, given this is our new node, we can actually set the new nodes next. Get that here to be actually where head is pointing at, which is here. And then we update head to point to the new node. Okay, so this is the start of our list now. So we're going to build our list like this. Where we update head. And tail can always be here, or you don't even need a tail if you're not planning on tracking or not inserting anything to the end. So this may not be necessary if you think about it. And so we insert 7, for example, we're going to create the node. I'm going to point that to head, the next pointer to head. So head, what is it? Okay. So new node dot next is going to be head, and head is now going to be new node. So that's the pattern. So head is now here. Now you think about this, if we follow this type of pattern here, that actually looks like a stack. So we had 5 before, then we inserted 6, and we inserted 7. That does remind me like a stack. And when you pop from a stack, well, really, you're just kind of taking the value here, saving it somewhere, and moving your head to point back to whatever that value's next node is. Okay? So that's the easy version of a stack. I think it's easier to do than an array, actually. So the advantage of this is that, well, with this type of data structure, you can keep adding things onto that stack. Whereas before with an array, we had a limit, a max size, because we didn't have any logic to grow our array. But now here, we're just limited by the amount of memory we have. We just keep constantly creating new nodes. But that also brings a lot of responsibility on us, because now we have to remember to free our nodes if we're going to allocate them in our heap. So there's a trade-off right there. Yeah, so like the more you allocate, the more you have to consider that you'll have to free at some point. So let's see. All right. So let's get started on coding and see how all this looks like if it's hard to kind of follow with diagrams. I might come back to it and draw more so that it becomes clear. But this is like a preview. This is like a preview of what a stack looks like. So first things first, we'll write our little template. And we're not going to really care too much about code organization or anything like that. We just want to get something working first, because again, we're building up our C skills here, and it's better to be able to express ourselves in C first before we try to have too much pressure on ourselves to create something that's like beautiful and something that the internet won't laugh at you for. So I don't care. I'm here to learn. So character RB. Okay. Okay. So that's like our basic template here. Now, I should probably go back and say that it's this. Like, these nodes here are individual nodes. What makes this a linked list is basically conceptual. It's a chain of these nodes connected together that makes it a linked list. There's no, well, really, we don't need a specific like data structure to hold these nodes. It's the nodes themselves that point to each other that make it a linked list. So I just wanted to clarify that, in that the chain of nodes itself is a collection. Kind of like how, with an array, it was a collection, but it felt more self-contained. This one is, with a linked list, it's not really, it doesn't feel contained, but technically it is, because if you think about all the nodes being chained up together, it is some sort of collection. Okay, so first things first, we need to define what our node looks like. So we can just define a struct, or declare a struct. So we'll do a type def, struct, node, and it's going to be a linked list of integers, as always. So we'll just do something like this. And we want to actually store a pointer to the next node. So we want to point. That's the whole point of a linked list. You're pointing to the next node. And then we're going to alias it as nodes so that we can create nodes. And so I also want to create like a helper function to print out our list whenever we want. It will be very helpful for debugging. So let's do a void print linked list. Or actually, let's do this. Void linked list print. And let's just do print linked list. Linked list. And we'll take in a pointer to the list. So we'll say node head. So we're going to then iterate through every single node and just print out the value. So yeah, so that's a simple thing. So what we're going to do is we're going to initialize a temporary pointer to point to the head, and we're going to move that across the list. So it'll just be something like this. So we'll go back to the linear way of doing this. So if our head is here, we don't really want to move our head like this because in case if we need to refer back to the head, we've lost it. We've lost the original location of where this node is. So I really like just having a temporary variable all the time and just moving that variable instead, so that if I need to reset the variable back to the head of the list, I will always have that reference to go back. So I'll have a pointer called t, and I'll assign that to head. Now, the main logic when you traverse through a list is you just want to keep iterating through that list until, basically, come on. Basically, t happens to be null. So iterate while t is not equal to null. So right here, you want to just print out every single value here. And when t becomes null, we don't do anything anymore. So that's an easy loop. So while t is not equal to null, we're going to just print every single node. So print f, let's say %d, and we're going to have a fancy pointer thingy here. And then we're going to then print out the value. Okay? At the end of it all, we're going to just print out null. So it's going to print out like 1, arrow 2, arrow 3, and then when it's null, t will then, t will be null, and it will get out of this loop, and it will print out null at the very end. And let's not forget to move our t pointer to the next value. Okay? So that's basically printing out our list. The next thing is we'll need to actually just play around and initialize our list by hand. So we can just say node first is going to be maybe 1, and dot next is going to be null. Let's say node second is going to be 2, null, and node third is going to be maybe 5, just to make sure we don't get thrown off with those easy numbers. And we're going to chain them together. First dot next is going to be second. Second dot next is going to be third. And then we could just say for safety, just third dot next is null. And let's print our list. Okay. Oh, we need to get the address pointer. So, there we go. Second, the next is a pointer to a node, so then we have to get the address of this node type, this node struct anyway. So that's why we need the ampersand. Okay. So now let's print linked list, and we're going to pass in a pointer to a node, which is going to be an address here. We're going to take the first node. We're going to see what happens. Okay. Why is this? Oh, is this just? What's going on? Should I refresh again? Yeah. Happens all the time. Okay. Okay. So now we have our code compiled. That's what happens. So 1, 2, 5, and a null. Let's make it a new line. Hate this. Keep forgetting that. Okay, let's get a clearer picture. Oops. There we go. So 1, 2, 5, and null. We have a basic linked list here. So this is a basic linked list that will print out this thing here. So every single node has some sort of content. So far, so good. Okay. Now, let's actually start writing some more stack-related code. So let's say this. How about we actually create a helper that will create nodes for us, like start to initialize the list for us. So I could tell that this is going to get a little tedious, where if we want to create new nodes or insert nodes, we have to like type all this out. So let's probably define, like declare and define a new function that will give us back a node given some value. So we can say something like this: pointer to a node create node int value. Okay. Now this is where it's going to get tricky, because we're going to have to allocate some memory and then return back the pointer. I'm just thinking on the fly. So then we can say something like node n is going to be, now let's include stdlib, because we need malloc. Malloc exists in stdlib. So we're going to malloc. How many size in bytes do we want to allocate? Well, we want to allocate the size of that node struct, because we want to be able to hold the value and the next pointer. So in memory, that's going to look like this. So we want to allocate in memory I like to draw, even though there's a rectangle. An int called value, and a pointer to a node called next. This is going to be 4 bytes, and this is going to be 8 bytes, because this is just a memory address. So all this is 12 bytes, and funnily enough, this is going to refer to maybe somewhere else in memory. For example, all the way down here, where it is also 12 bytes. And somewhere here is you're going to have another pointer, node next, that also points somewhere else in memory that is going to occupy 12 bytes. And maybe that one is going to point all the way up somewhere that occupies 12 bytes. So this is 8 bytes holding the memory address to the place where the next node is going to start. So we can get that size, this total size here, using the size of operator on that data type. So size of node. And we actually want to cast this because malloc returns a pointer to a void. We want to cast that to be actually a pointer to a node struct type. So now that we have that, we can actually then assign a value to that node and also initialize its next value to null. And we can just return that node. Okay, well, we have a node created, but now we need to also remember to free those nodes. So then this is another common pattern in terms of freeing every memory or every portion of memory taken up by each node in the linked list. So let's say you have your linked list here, and all of them were malloced at some point. So let's say our head is here, and we want to actually start to free up memory. If we were to free this directly, head directly, we would have lost our link, and we can't free up the rest of these nodes here. Where would we go? We got rid of this. Well, we got rid of head. Now what? We've certainly freed up this memory, so this is 12 bytes, this is 12 bytes, this is 12 bytes, this is 12 bytes. We had 48 bytes allocated, but then we weren't able to free 36 of them because we lost our link. So again, going with that traditional pattern of iterating through a linked list, get my pen back. If I had head here, what I really want to do is have a T here. Okay? And what we're going to do is we're going to first assign T to be head. Then we're going to assign head dot next. Oops, head to be. Ooh, thinking ahead. We're going to assign head to be head dot next, which is going to be the next node of itself. So basically, before we do anything, we're going to do this here, where we move head here after we assign T to be head. So then when we free this, we're actually going to be calling free, instead of head, we're going to be calling free T. So it'll free whatever T is pointing to. Okay? So then what that means is that the next iteration, we can actually repoint T to head. So just like what our code is saying here, T equals head. So we're going to point this to where head is. And then we're going to reassign head to be, well, head.next. After that, we free T again. Okay? And we move on to the next iteration. Oops. Where we assign T to be where head is. Again, we take head and we move that up one to its next pointer. And then we're going to free T again. Okay? And we're going to move T to be where head is. And then we're going to set trust the process head to be where it is next. Okay? Which is null. Just trust the process. Then we're going to free T. And then we're going to set T to be where head is. So now T is null. We can't really then move head next because head has no next pointer at this point. Even though we set T to head, this is where it's going to fail. So that's why, it's right here. That's why we're going to have a while T is not equal to null. So we're going to basically do all of this while t is not equal to null. As soon as t is null, that means we freed all our nodes. So that's like a general idea on how we can actually free every node in our linked list. So we can do this. Void free list. And we'll start out with a pointer to the head, and we initialize basically another pointer at head, and then we'll have a loop while t is not equal to null. What we're going to do is first we're going to assign, okay, well t is going to be head again, and head is going to be head.next, and we're just going to call free t. Oops. Okay, it's an arrow because it's a pointer. So that's how we free our list. All right, that's cool. So how do we test this? We can create some nodes using this create node call, and then we'll do like, let's say, I think I did my example showed 4. Okay, 4 nodes. We're gonna create 4 nodes using this create node here because it's gonna call malloc. We're gonna stitch them together, and then we're gonna free our list, and we're gonna test that using Valgrind. So let's do it. I am going to then just remove that, and maybe remove this too. Remove everything. So we can say create node. So let's say node star first is going to be create node. This is our helper now. 1 node star second is going to be create node 2. Node star third is going to be create node 5. Node star fourth is going to be create node maybe 9. Then we're going to stitch it together. So first, next is going to be second. Second, next is going to be third. Third, next is going to be fourth. And then fourth, next, just for sake of pattern, it's going to be null. And we'll actually print our list. Let's just print our linked list. Okay? It's going to take a pointer, so conveniently we just pass it like this without the ampersand because we already have the address. This is actually a pointer to a node, so an address. I'm going to print that out. And actually, let's see what happens. Let's see what happens if we don't free. Well, let's compile and print out our list. That works. We were able to print out the list. We have everything all created using the create node. But what happens if we compile this with debugging information, and then we use Valgrind? I think it's leak check equals full a.out. Okay, so we have something interesting. So Valgrind is going to run our program, and since our program just directly creates the nodes using malloc and actually chains them up together here, and then it will run the part where we print out the list, it's going to report us some information. The leak summary is given to us here. It says, well, you definitely lost 16 bytes. Okay. I am guessing my estimation of 12 was wrong because maybe there's like padding or something. I don't know. Maybe. Actually, I'm curious. What is the size of size? Size of it is 4. So there must be padding to make it 16 bytes. Anyway, we lost 16 bytes and we indirectly lost 48 bytes. I wonder where 16 is coming from. Maybe from somewhere else. I don't know. Something's extra. 16, 16, 16. Oh, 48, yeah. So we lost this one indirectly, but we for sure lost one of these. So that's our memory leak. So total bytes, we lost 64, which is pretty much everything. It says what bytes in one blocks are definitely lost in the lost record 4. Okay, so yeah, we lost everything. 64 bytes in 4 blocks. Okay, so what happens if we free our list? Starting at the head of the node, which is first. Let's see what happens. So let's compile again and run Valgrind. Okay, so now what's going on? Well, we're still wasting memory. 1, 2, 3, 4. And we still lost memory, but less. So there's something wrong with our code in free. I wonder what is wrong. Well, let's see. Well, head is going to be head next while t is not equals to null. Okay, so let's do this. Let's debug by hand. This is the reason why I like doing this live. So what did I do? I allocated 1, 2, 5, 9, and let's kind of trigger that there. Null. And I say I passed in this one as head, and I've assigned this one as t. Okay? So at this point, we're good. Okay? So while t is not equals to null, okay, well I assigned t to head already. That's cool. Now head equals head next. Okay, so then we'll move head to be here. Okay? And then we'll free t. Okay? What's next? Well, now t is reassigned to head. So let's take my eraser here. And let's assign it to head. Sounds good. Okay. Should I? Oh, maybe. Okay, let's see. Okay, so now t is head. Head is going to now move to next. It'd be easier if I wasn't so clumsy. Okay, and we'll free t, whatever t is at. Okay, we'll trust the process. Now, we'll assign t to be head again. Maybe. Let's see. Because t is null at some point. I think it never executes. I get it now. While t is not null, I'm not sure if that's the right one. Why? Because every time we free t, what is t? What is t after free? Good question to ask. So I realized that every time I break that link, technically, what's going on? All right. So technically, every time we free, okay, every time we free write this, at some point, what is t? At this point, when we call free t, what is t? Is that null? Let's actually check that. So what is t when we free it? C. Printf. And let's just do integer to test And if we get a 1, that gives us a hint. Essentially what we want to do is we want to test to see if t is null. And this should return us back some sort of boolean. So 1, if it's true, yes, it is null. 0, if it's not null. So it's live programming. Make mistakes, and that's that's how it is. Okay, so we're gonna run our program again. This time I'm just gonna run the program as normal. Did I even compile? Interesting. What happened? Oh, free list, not free. Another bug. Maybe it was working all the time. Let's see. Okay, segfault. So there is something wrong. So first, I had a lot of bugs. The first bug is I didn't call free list. I didn't call the thing I made. I just called free. I did this, which of course is only going to free the first node. I should have called what I created up here, free list. And the second thing is, now I don't know if this is actually working. Let's see. Segfault, because t is never null. T is never null. Oops. So I'm accessing null. Well, I want to check for null, but it's never null. What's going on here? So, is a condition to check while t is not equal to null? Or should we be checking while head is not equal to null? Let's see. Interesting. That works. Well, when we free t, what ends up happening is that we get garbage. Okay? T becomes garbage after we free t. And then when we check t here, well, t is going to be not equal to null anyway because t is pointing somewhere else in memory after free. We're just marking, right? It's just marking it as available to be reclaimed by the OS, but it's not technically null. So when we free t, t is still not equal to null, but head is, because head at some point is going to be null. So what happens then if we compile that again and run Valgrind? Whoa. Okay. Heap summary. All heap blocks were free. No leaks are possible. So that's pretty good. I mean, I personally messed up a couple times, but I'm glad I did because that allowed me to think a little bit more about what I was doing. I was so confident when I was drawing, but my drawing was not really thinking about exactly what could go wrong. And it's what could go wrong is that, well, you free t, but you're asking whether or not t is null or not yet. And of course, it's never going to be null, so it's kind of like an infinite loop in this case. It just happened to have crashed before that case. And the next thing is that we actually looked harder as to what was going on. Like, why? Well, free is actually a valid call to reclaim the node. It's just that we only reclaimed the memory used by one node because free is just normally just free. It just frees whatever you give it. Whereas free list goes into the function that we created here and iterates through every single node in our list. So yeah, so we were able to free all our memory that way. Again, I think since last time we learned about how to use this, and I recommend that this is a good way to kind of check to see whether or not you're doing these types of motions correctly. This is literally like the third time I've ever used Valgrind. First with the book, second, which was last time with the stack array, and now this time. And I'm starting to really like it. It's yeah. Anyway, okay. Well, so now we have the basic thing of creating a node, and we can be assured that we could free our nodes. So at least we can start creating a stack in this case. Again, a stack will just have push, pop, top, and is empty. So let's write our function list here. Push, that's going to take in a value. We'll have pop, which then returns a value and modifies the stack. We'll have top or peak, which will then give us back a value, but doesn't modify stack. And then we'll check for is empty, okay? Which will return us true, false, or yeah, true if empty, false if not. Okay? So basic stuff. Basic stuff. This time, since we have a list, we actually don't need some sort of top index anymore. Why? Our top index is actually going to be the head of our list. The top of our stack, basically top index pointed to the top of our stack. The top of our stack is essentially going to be the head. So we can just pop and update, well, I first update the top first, and then pop the value out. That's easy. Therefore, at some point, if you keep popping, the top is actually going to be null. And that is what is empty is checking for. Is empty is checking for head is equal to null. That's it. If the given head is null, then you have an empty stack. So let's do that. That's going to be the first one. Include std, or is it bool? Std bool. Std bool.h. And we'll say bool. Let's put it down here. Let's actually put it down here. Bool is empty, taking in the head as a pointer. Return head is null, or not. So, our signature here is empty. Returns true if this given stack is empty. False otherwise. Okay. Done. Easy. Easy. Next one, let's do peak. So that's gonna be easy too. So return us back a integer. We'll call it peak, given some node head, and we're gonna return head value. We don't alter the stack at all. That's all there is to it. Returns the top of the stack, but does not remove it. Remove the value, okay, from the stack. Okay. Next one. Let's do pop. Pop is going to return the value, but also modify the stack. Okay, so let's just return the value. So node head. First, let's keep it temporary because we're going to move our pointer, right? So node t let's call it result node. It's going to be head. And we'll set head. We'll move it basically to the next node. And then we'll return result node dot value or value. But this is kind of weird because now we're going to lose our reference to the previous node and we have mallocked it. We have to free our result node actually. This won't work because if we move our head to the next, but then we have this node, other node that used to be the head floating around, we'll return that value, but it's going to be hanging around memory. We have to clean that up. So instead of actually saying result node, let's say prev head is going to be head. Head is going to be head next. And then what we want to do is int result prev head value. So we're going to say, well, we're going to have our result integer going to be the previous head value, the one that used to be the head, the top of the stack. And before we do anything, we're going to free basically the prev head. So we're going to move that dangling node from memory. Okay? And then we're going to then return result. So little dance that we have here. So we're going to say remove the node from memory or heap. Okay? It is dangling. It is dangling. Yeah. Okay. Alright. Cool. Push is just going to be using our create node, given some value, and then just setting that as a new top of the stack. So it's like inserting the node into the list, basically, but that node becomes a new head. So we'll say void push. In fact, let's do this. It'll return us back the new head the new head of the stack. So node push. We need a head. So basically the topmost element and the value we want. Okay, so we're going to let's do this. Let's just actually comment this first. Pops returns the value at the top of the stack and modifies it. Yeah. Oh, and removes it from the stack. Okay, clear it up. Okay, before we forget, push. Pushes the value to the top of the stack, returns a reference to the top of the stack back. You'll understand why that's important. Okay, so we'll say node n is going to be create node with the value. And then what we're going to do now is we're going to say, well, n next is going to be head. So now n is going to be at the top, pointing to head. But now head, okay, can't be the head anymore. So head has to be n now. So we have to move the pointer that is referenced like head. We have to move our head pointer to the node that we just created because that should be the new head now. Okay, and we'll return head. So we'll return that. Okay, and that looks like it is complete-ish. Except, notice how for pop and peak, we actually don't check for an is empty. Because we're going to be popping and peeking into nothing. And that's very dangerous. So let's actually add a check. If head, or let's do this, is empty. Okay, head. We're going to say if printf, we're going to go to stdr, cannot pop an empty stack. And then we're going to exit what? Same thing here, cannot peek at an empty stack. If is empty, head. We're going to print f cannot keep at an empty stack. Okay, and we're going to output that to SD and we're going to exit. And since we're now referencing is empty, this cannot go down here anymore because then that would mean that we're using a function that we haven't declared. So now this is going to the top. Okay, so now when we call is empty, it knows that it exists because we have declared it. And I think that's it. That's a good first pass, and let's see what bugs we'll get. Okay, so let's do this. We'll say node stack, node stack. Okay. Push. Let's do this. Push. If head is null, that means if we don't have anything, it's an empty one, then head is going to be the one that will be the new value. And we'll just return head. Like this. Short circuit. That's if we start with the empty stack. So empty stack here, and we'll say stack, oops, print stack, and let's push. Push, head, okay? Or not head, stack, 1. And also stack needs to be reassigned, because that's going to be the new top of the stack. Then we're going to say stack equals push stack 3. So now we have 3, 1. Stack equals push stack 5. 5, 3, 1. Push stack 9. For some reason I don't like the number 7. 9, 5, 3, 1. And then we're gonna print this and we're free stack. So we're gonna print whatever's on top of our contents of the stack. So again, here, 9, 5, 3, 1, null. That's cool. So then we can actually then do this. While not is empty, so we're going to keep popping from the stack and print each value. While not is empty, stack, we're going to say int pop stack. I'm going to print f popped, and I think that's it. Ooh, double free. Of course, because we're trying to free. We've already freed everything, so that is an automatic free because we freed while we were popping. Right here. So technically, we're trying to free something that was already freed. So let's just do it this way first. Oh, where is that coming from? Double free detected. Why is that? Did I compile it? Where's our double free coming from? Oh, is it because this is actually... interesting. Oh yeah, I got bit again. Damn it! Dang it! So this is actually passing in memory just by value again, right? And then we're modifying our value here. Again! So it's important to remember that when we copy by value, how should I say this? When we copy by value and we're going to modify wherever that value is, basically reassigned. Of course, it's going to go way after the function ends, right? So it's no different when you pass in a pointer that pointer is a memory address, which is like basically a number. And when you call the function with that passed in, it's going to copy that value. And so, boom, when I do assign head to head next here, what's happening is that I'm just modifying the copy of that pointer. Okay, so in memory, it looks like this. Bad drawing. Okay, memory, it looks like this. So I have head here. So I'll have head. This is my original head. Okay, and basically here is my struct in memory. So we'll have maybe, I don't know, I said it was 9, right? So int value 9. And that's like, let's say this is like memory address 300. And then this is also next. So node star next. It doesn't matter where this is pointing to. It's just, it goes to the next node. Okay, so basically, and let's just call this 304, something like that. This one, let's say, is 101. Okay. When we actually call the function, we're going to actually copy over the head here. So, and again, this one here, at this point, is a pointer to this struct here, so it's going to contain 300. Okay? Now, this one that we just copied is the same thing, 300. It's a pointer type. So technically, we dereference this one here, right? Dereferencing this pointer here will lead us to here. But if we dereference that, we'll be back here too. So that's why it works. Except that when we call that function, it's probably a copy. So we can do two things here. Two things. We can instead pass a double pointer. Then we can dereference that. And then dereference our head and reassign it this way. Okay? And then this will actually be also dereferenced. And this will also be dereferenced. We can do that. Okay. So that's the double pointer. So now let's just let me try to work on this first and then let's see. So what instead? Okay, well, if stack is a pointer, how do we make it a double pointer? Well, you want to get the address of the pointer. So this is a pointer type already. And when you get the address of that, you're going to basically turn it into a double pointer. So you have a pointer, you have a star, right? And then you get the address of that, and now you have a star star. So where are we at? Star star. So we're gonna modify. So we're gonna dereference that double pointer to check to see if the real pointer here is empty, and then we're going to dereference again to get the previous head, that pointer, and then we're going to move our pointer after we dereference that double pointer to the next node. And then we can just, since this is already a single pointer, after dereferencing it, we'll just get the value, and then we'll actually free that, and then free that memory address, and then we'll return the result. I don't know. Ugh, scary. Yeah, so it works. I wonder if it leaks memory. Let's see. Clean! Okay, so why does that work? Alright. This will be the last thing I explain, and then I have to sign off. But why does that work? Well, so let's say again, we have memory 101 because I don't want it too perfect. And we had a node here, and we call that head, okay? And the memory address here. And then we'll have our struct in memory. Value, and we'll call that 300, and we'll say that's 9, and then we'll have yet another pointer to a struct called next, and then that is maybe, I don't know, located at 400, something like that. Well, when we call our function here, okay, we're going to make a copy of that head, and this will be probably like maybe 105, 4. I don't know. Maybe let's make it easier so I don't bite myself. 200. Okay, so this here, what does this contain? Well, this is the address to where the struct starts, so it's at 300. Okay, well now this one, it used to be a single pointer, but we're going to turn this into a double pointer. Now, that means instead of passing in 300, there's a single pointer, right? Pointer to that struct. We're going to pass in a pointer to a pointer to the struct. A pointer to the pointer of the struct. So what value is this? It's not 300 because that will be the pointer to the struct. We want to pass in the pointer to the pointer to the struct. So actually it's the address of this one. Okay, so it'll be, just do that, 101. So when we dereference, we want to take this value in here and we want to trace it back to the value in this memory address, which is 300. Okay, and that's what we did here. That's what we did here. So then, whenever we mess around, for example here, we dereference that, we're going to then, let's say the next node was 400. Well, guess what? We dereferenced right here, updating it with the next. So since we've already dereferenced, we're here, we get to say, well, now that's 400. So that's why it works. And when we free, well, we had already dereferenced the 300 right here, so we were able to get that, and we can just free that. So it's like that extra level of indirection, a pointer to a pointer. I can explain that in more detail in the next video, but I have to sign off. Yeah, I hope this wasn't really like too confusing. I was personally confused for a little bit in some parts, like freeing the memory and this double pointer stuff. But yeah, let's take some time for it to like bake in. Anyway, thanks.